Welcome to the Crazy Head Chemist. So here we go again. Today, 16th video. We're getting close to the end on atomic structure. Bam! So today we're talking about isotopes of elements here. So an isotope of an element has the same atomic number, that's the same number of protons, but a different number of neutrons and therefore a different atomic mass. Most elements occur as a mixture of isotopes. What about their chemical reactivity of isotopes of the same element? We're going to answer that in just a little bit. And then what about radioactivity? Are all isotopes radioactive or not? We'll find out here in just a second. So here's a little diagram of hydrogen. Okay, so this right here in the center of the nucleus is a proton. And this right here on the outside of the nucleus is an electron. Notice that this is hydrogen, and so it has the A for the mass, which is the sum of the protons and the neutrons. And this is the Z, that is just the number of protons. Now, this is the only element of an only isotope that does not have any neutrons in it. Okay, and it is a set of isotopes that actually have specific names. It's the only set of isotopes that actually have names. This is protium, which is otherwise known as hydrogen 1. Okay, here is deuterium, otherwise known as hydrogen 2. And in deuterium, the difference between hydrogen and hydrogen 1 and hydrogen 2 is that there's a neutron inside the nucleus in deuterium. That's hydrogen 2. So therefore, the mass is actually twice as massive. And there's actually a third isotope of hydrogen, and that is hydrogen 3, or tritium. Okay, and you should see that there are 2 neutrons in there and 1 proton in the nucleus. Therefore, that's why the A, the atomic mass, is 3. But you should see that there's a consistency here with the isotopes of hydrogen, and that they all have the same Z number. That is, they all have the same atomic number, which is the number of protons. However, the number of neutrons varies, and therefore the masses differ as well. However, you should also see that the number of electrons remains consistent in all of them, and that hints to the chemical reactivity, which we'll discuss in just a second. Here is another set of isotopes as well. This is copper 63 and copper 65. Okay, and you should see there's something consistent here, and that is the atomic number for copper is 29 for both of these 2 different isotopes. However, the number of neutrons differs, and that's why the copper 63, copper 65. These are the only 2 naturally occurring isotopes of copper. They occur in a roughly 30-70 mixture, percentage-wise. Okay, you should see that this is the A, this is the atomic mass, that is the sum of the protons and the neutrons, and this is the Z, that is the atomic number, that's the number of protons. In fact, since these are neutral elements, it's also equal to the number of electrons. So here I've delineated here for you the number of protons for each, that's 29. The number of electrons for each is 29 as well, because they're both neutral. Now, copper 63 has only 34 neutrons, where copper 65 has 36 neutrons. Okay, hopefully you see that there's a difference in 2 neutrons. That's why the mass differs in 2 as well. So, chemical reactivity. What is responsible for an atom's chemistry, really and truly, as far as chemical reactivity? It's actually the outermost subatomic particle, which is the electrons. So, if you look at all the hydrogen isotopes, there are 3 of them there. Are the electrons the same or different? They are the same. Therefore, their chemical reactivity is the same. Take a look at the 2 isotopes of copper. The number of electrons in the 2 isotopes of copper are also the same. And therefore, their chemical reactivity is based on the number of electrons, and they are the same, and therefore their chemical reactivity for isotopes is also the same. Okay? However, radioactivity. Is protium radioactive? No. Deuterium? No. But tritium is radioactive. In fact, it's the only isotope of hydrogen that is radioactive. Copper 63 and copper 65 are not radioactive. So must there be a radioactive isotope in a set of isotopes? Absolutely not. That's not necessary. at all. Okay, let's keep on going here. So here's an isotope analogy for you. So here are two pickup trucks. They're by the same manufacturer. Those are Toyotas. So they serve the same function. That is, they're both pickup trucks. They can carry heavy loads, except their masses differ. So I have their two masses written down there for you. The Tacoma is less massive than the Tundra. So hopefully that makes sense for you for an isotope analogy. Same function, that is the same number of protons, same number of electrons, but their neutrons differ. That is, their masses are different. Okay, here's another isotope analogy for you, and these are hammers. They're the same element, they're all hammers, but they have different masses. You should see that some of these hammers are bigger than the other ones. They do sometimes serve different functions as well. Even though they are all hammers in the second picture there, some of these hammers have different functions than the other ones do. Okay? Hopefully that worked well for you for an isotope analogy. So, same atomic number, but different number of neutrons, so therefore different masses. I am the Crazy Hat Chemist, and I got a crazy hat here. I am an elf today, and too bad you can't see my shoes, because I got elf shoes on too. Give me a thumbs up if you like that video, and subscribe to my YouTube channel, and I'll see you next time. Bye now.